Common Core Geometry, Unit 6, Section 1, Scale Drawings. So first of all, let me apologize for my voice. If you saw me in class today, I could barely speak, but I needed to get this video done, so I'm going to try to power through it. But I apologize if you have trouble understanding me. So this chapter is called dilations, and this is the first time that we're talking about that. We've talked about all the transformations before, and with the rigid motions being reflections, rotations, translations, which led us to produce congruent images. And that's really what the first 5 chapters of this course were all about. Was we started with constructions and then a little bit of algebra and then those rigid motions which helped us produce congruent images, and then we were proving congruent images. Well, now we're finally going to talk about dilations, about changing figures sizes. They're still going to be the same shape, but we can make it twice the size, 3 times the size. But it's a scale figure because there are some properties that are preserved. The size is not preserved, but some other properties are. And so it is a transformation, a dilation, and we're going to see what that is. And this is a construction chapter, so we're going to start with constructions and then do a little bit of algebra and stuff like that. And eventually we'll have some minor similarity proofs. We'll still see some rigid motion stuff, but maybe using reflections, translations, and now dilations to prove things are what we call similar, not necessarily congruent. But all this is going to be explained in various videos. This one is really just kind of an introduction on how to produce what we call a scale drawing. And really it is kind of like a dilation of it. Like I want to make this triangle, same triangle twice the size, or same triangle half the size, things like that. So some of the terminology is we have a scale factor, is the ratio, and we use the letter R, of any length in a scale drawing relative to its corresponding length of the original. So like if we want to do a scale drawing where R equals 2, that means we want to make it twice the size. So if R is greater than 1, then the figure will increase in size. And if R is less than 1, or between 0 and 1, then it's going to decrease the size. We never have a negative ratio. That's why it's between 0 and 1. Like you're never going to, do a scale drawing where R equals -2. That doesn't really make any sense. I can make the triangle bigger, like twice the size, or I can make it smaller, like half the size. It doesn't have to be 2. It could be a quarter of the size, a fifth of the size, but it's never going to be negative. If R equals 1, then there's no change in size, no size change. It might produce, maybe I'm drawing a second triangle, but it's the same size. But um, our scale drawings will be one of these two today. So the properties. So we obviously know that the side lengths will change, but corresponding angles in measure do not. Corresponding angles are equal in measure. Corresponding angles are still congruent. So we still have all the angles congruent when I do a scale drawing or a dilation. But the lengths are obviously not the same size. If I make something twice the size, then the lengths are not twice the size. But there is a very special, very important length property, and that is that corresponding lengths are proportional. And that's really kind of the big key to the entire next couple of chapters, is that the corresponding lengths are proportional. So when I make a triangle twice the size, whatever my side length was, my new one is, well, it's double that because my ratio was 2. And so it's twice the size. So we're going to see that. Let's see a couple of constructions. So use your construction tools to create a scale drawing of triangle ABC with a scale factor R equals 2. And so what that means is I want to make it twice the size as this. What do you notice about something? So the first way I want to show you how to do this is with an overlapping figure. And so we have to pick an angle we want to keep as the angle that's not going to move. And let's pick angle A as the angle that's not going to move. And I'm going to draw a figure twice the size with A still there. Like A prime, our new A, is going to be at the same location as A. And so what we want to first do is just take your straight edge and extend these sides. Now, if I want it to be R equals 2, just estimate what 2 is and go beyond that. Just go well beyond R equals 2. Oh, way beyond 2. Don't go too short because it needs to be at least 2. But so this looks like it's maybe 2 is going to be somewhere over here, 2 is going to be somewhere over here. But I don't need to estimate because our compass can do that for us. So this is actually very easy. Just extend those sides And if I want it to be r equals 2, well, I have to figure out what is the length of AB. So just set your compass to be the length of AB. And anytime we measure something, we make a slash. And then where that slash is, put your pivot there and make a new slash. So this length here is double this length because I set my compass, did one mark, and then I moved it over and did a second. So it's 2 of AB lengths. This is where my location of B prime is going to be. And that's A prime. So AB is that length, A prime, B prime is double that length because it's 2 compass marks of the same length. Now we'll do something similar for AC, except it'll be a different length because it's a different triangle size. So let me expand this to be side length AC, make a slash, go there, and make another slash. That length is now double AC. So A prime didn't move. This is my new C prime. And make points, not just slashes, when you are where you need to be. And if it said triple, then I would go and I would make slashes 3 times, 4 times, however the times it means. But now that I know these sides, I can take my straight edge and connect that. So there we have it. That's it. So this big triangle is triangle A prime, B prime, C prime. Let me just highlight it for you a little bit so you can see. So that this triangle here, A prime, B prime, C prime, is twice the size of triangle ABC because I took the side length of AB and I doubled it. I took the line of AC and I doubled it. And then that produced that image. So they're kind of on top of each other, but that is a scale drawing of twice the size. So what do we notice about a couple of things? What are they saying? What do we notice about AB and A prime, B prime? Well, it's twice the size. That A prime, B prime equals twice the size of AB because we had a ratio of 2. And what do you notice about the measure of angle C and angle C prime? Well, even though the triangle got bigger, the angle measurements did not change. Because these angles are congruent, their corresponding angles congruent, that actually also means that these sides are parallel. So these sides, are on top of each other. They can be kind of thought of as parallel, same slope, same thing here. It's the same because the angle measurements don't change. These sides are definitely parallel. And so let me write that down too because that's very significant. That CB is parallel to C prime, B prime because of corresponding angles congruent. So the sides are proportionate, and a proportion of 2. That I don't have lengths here, but if I did, if I said that, this length was 8, well, then this length would be 16 because it's twice the size. And the ratio of these sides is 1 to 2, the ratio of these sides is 1 to 2, these sides 1 to 2, and that's really what's important here. A couple more quick ones. What if I want to go half the size? Well, I just need to pick 2 sides and make them half the size. And how do I do half of something? We do our perpendicular bisector for half. So extend a little bit beyond halfway and draw some arcs. And I'm going to flip it around. Same thing over here. Draw some arcs, kind of going into the next problem a little bit, but that's okay. Make a point there. We've seen so many perpendicular bisectors, we can do this quick. And we'll do this side next. Flip it around. Excuse me. And where they meet, we'll do that. Make a point there. And then I can connect those. And so now, since this side was half the length and this side I made half the length, that means that this triangle over here is half the size of my original big triangle right there. So it's basically what we did here. We doubled the sides. I'm sorry, I gotta scroll down. We doubled the sides here. Connected here. I halved the sides. And let me label these points appropriately. Z didn't move, so that would be Z prime. This is my new X prime, and this is Y prime. So the enlarging with R equals 2, that's definitely easier. Just, expand the sides. Here we have to do actually perpendicular bisectors to make something smaller. One last one. Here, I'm not giving you a scale factor. So I want a scale image here, and I'm going to say this is the length of side AC. I don't know if it's twice the length or 2.5 the length or 3 times the length, that doesn't really matter. But I want whatever this ratio is from this side to this side, I want the other triangle this side. So how can I do that? Well, one thing we know is that the angles aren't going to change, right? That whatever angle A is, that's still the length here. And so I can copy my angle. So let me get my compass down here and copy the angle for A. And so we go to the pivot. So a lot of these constructions, this is a construction chapter, but we're still using all the same constructions we've learned prior. So make an arc and then draw that same arc, make sure it's big enough. I'm estimating it's going to be over there, so make sure it's big enough. And then I need to measure the arc. So put my compass one spot where it crosses and set my length to be the other spot. And let's see, is that, yeah, it's pretty good. And make a little slash, because we always have to make the slash for measuring. And do the same thing there. So that's one angle copied. Okay, now let's measure, and then I can connect those points with my straight edge. Right there. Excuse me. And let's do the other one. So again, I'm going to make this a little bit bigger, easier to work with. Draw the arc for angle C. Same thing over here. And then measure it. Measure the separation. Set the compass for the separation, make a slash. Oops. And then that's it. And then I can copy that angle with my straight edge, and where they cross, that's going to produce my triangle. And so that is going to be my B prime. All right, so we'll practice all of this again tomorrow, but the keys here, and I know this video is a little long, the first one in the chapter is always a little long, is this stuff right here. Whoops. That the angles are staying congruent, but the sides are staying proportionate. This is huge. And to expand, I could just expand the sides, or I can, make it smaller by doing bisectors, or I could just not even give a scale factor. And in this one's saying determine the scale factor. We can measure this and see how many it fits, but we're running out of time here, so we'll do that in class. But if I give you a length, well, I know the angles don't change, so I can copy those angles and see what happens. I'll produce a scale image that way also. All right, so this is kind of the intro to dilations, and we're going to see more constructions similar to these. See ya.